Welcome to SingleCrystal 4. In this tutorial, we're going to take a look at twinning. Twinning is a very common phenomenon caused by mistakes during crystal growth or as a result of a displacive phase transition where symmetry is lost and different regions of the crystal which were related to each other are no longer related. For example, consider a cubic to tetragonal phase transition where the unit cell becomes stretched along one axis. On a macroscopic level, different regions of the crystal stretch in different directions, which serves to minimize the overall strain. Now, these different regions are called twin domains, and where two twin domains meet, we have a twin plane, a coherent interface where the lattice matches exactly. In this example, you can see that the twin plane is parallel to the lattice plane 101. Now let's see how this affects a single crystal diffraction pattern. Here we have a tetragonal diffraction pattern for a potassium aluminosilicate called lucite. This mineral crystallizes at very high temperatures in the cubic system, but transforms to a distorted tetragonal phase on cooling. We can see that it's tetragonal by looking down the y-axis, the 010 direction, and we'll use the orient command to specify this. You can use the stereogram as a quick guide. So here we have the x-axis, the normal to the 100 plane, horizontal, and the z-axis, the normal to 001, vertical. And we can measure some distances by shift-clicking on the reciprocal lattice points, and we can compare those distances along the x and the y directions, and you can see that the directions are subtly different. This distortion in the unit cell results in twin domains, which have twin planes 101, which is a pseudo mirror plane. Diffraction patterns are the superposition of two orientations, and we'll now investigate that. I'm going to rotate the crystal so that the 101 direction is vertical. Now to do that, I'm going to measure the angle between 101 and the horizontal. So let's shift click on three reflections and get the angle between them. That's 43.5 degrees. And we're going to rotate precisely through 43.5 degrees by using the rotator. So let's type in an angle. I want 43.5 degrees. And let's rotate that. There we go. So 101 is now horizontal. Now next, I need to duplicate this pattern so that we can replicate the effect of two different orientations in the same crystal. Now this is easy to do. We'll go over to our patterns list here on the left hand side, and I can duplicate a pattern. If you just right click, then we can tell the program to duplicate. And let's give this a new name. So let's call this lucite domain 2, and let's call the first one lucite domain 1. You can edit these names by selecting a pattern and hitting the return key, or you can just click on the name and start typing. Now to distinguish the two domains, I'm also going to change the color of the two domains. So let's go for blue for the first domain. We'll go over to our inspector. I can do that by letting the inspector slide out, and we'll go to the display inspector and let's choose blue, and let's change the color of the second pattern and let's make that red. And we can overlay the two patterns by shift clicking, and now they're overlaid. Of course they're in the same orientation currently, so we need to change that. Now in order to change one pattern or relative to the other, I need to lock the pattern whose orientation should be fixed. So let's move over to the title area and I'll click the lock button for domain number 1. Now domain number 2 is related to the first twin domain by a reflection in 101. We said that 101 is the twin domain. So I'm going to replicate that by rotating the pattern through 180 degrees about the screen y-axis. So let's go back to our rotator, and we're going to rotate about the screen y-axis, which is the axis that runs from the top to the bottom of the screen. So 180 degrees. And now we have our rotation. Notice that our composite diffraction pattern, which shows contributions from two separate twin domains, contains pairs of spots except along the 101 direction, where the spots match exactly. That's because the 101 plane is a coherent boundary between the two twin domains 1 and 2. I'm going to tidy this up slightly. We're going to hide the labels, and now you can see more clearly that we have reflections matching exactly along 101, the 101, 202, 303 directions, and they start diverging as we move further away. If we look over at the stereographic projection on the right hand side, which we can resize, we have two sets of orientations for twin domain 2 and twin domain 1. Now we can actually tidy up the stereogram. What we'll do is we'll go to the inspector and we'll go to the poles inspector, and I've got domain 2 selected. I'm going to color by pattern, and I'll select twin domain number 1 now, and I'm going to color that by pattern as well. And now we can see we have got poles for domain 1 on the right reflected over onto the left to give us poles for pattern number 2. So these are mirror images, and you can see the pairs of spots. Now, how does this happen in real life? This is a nice simulated pattern. Well, we can compare this pattern with a real observed diffraction pattern for the same crystal. So we can move to our desktop, and we have here an electron diffraction pattern that shows split spots. I'm going to drag that into my window. Let's hide the stereogram, and here is my observed diffraction pattern. And we can change the color of this. This is nice and colorful. Let's just change this to a grayscale display, which will invert. And we can rotate this relative to our screen axes. There we go. Now I've already set the wavelength and the camera length, and the resolution of this image is embedded in its metadata, and that's been recognized by the program. So we can now overlay one set of twin domains on our observed pattern, and notice that the red spots line up over the observed black spots exactly along the 101 direction and exactly along one of the sets of pairs perpendicular to that. Now if I now shift click on the first twin domain, we now have the blue spots covering the other set of black spots. If we zoom in, we can see that more clearly. So we have twin domain 1 in blue and twin domain 2 in red, and combined we get this pattern of doubled spots perpendicular to 101. So that's an example of using SingleCrystal 4 to understand twinning in a real crystal.